Welcome to the second AP Stats Quideo. I'm starting here with the basic question. So we are given various times that it took Professor Moore to swim 2,000 yards, and his pulse was recorded after each swim. So we have the data of the various times and pulse rates right here. So the first thing that the problem is asking us to do is to verify that a linear model appropriately models the data, and then we are asked to state the equation of the linear model. So on paper I actually graphed this out, and we can see that it definitely does appear to be linear in shape, specifically with a negative correlation. So I went ahead and put the data into my calculator here, and then I went ahead and calculated a regression line, and it reveals a correlation coefficient of about negative 7.6. So that's a fairly strong relationship here that we can see from that variable. And then it asks us for the equation of the line, which the calculator simply gives to us. And each variable, the x value in your equation being time, the explanatory variable, and the y, or output, being the pulse rate, because the time is presumably the thing that is determining what the pulse rate is at the end of the swim. As you can see, if he takes a short amount of time, his pulse rate will be higher, and if he spreads out the swim over a longer period, he will have a lower pulse rate. So they're inversely proportional. We can tell all of that from the equation. And then just to verify, I put the regression line into the calculator, and we can see that it definitely is modeled linearly fairly well. Part B of the question then asks us to predict the pulse rate given our regression line, or least squares regression line. So that's simply as easy as just plugging in that time, 34.3 minutes, into the equation that we got here. So time being our x value, our explanatory variable. When this is plugged in, we get 147.4 beats per minute, which is about 4.6 away from the real value that it gives us of 152, which is I'd say a fairly accurate prediction, considering the pulses range from about 124 to 156. There's a fairly large range, so about 4.6 away is not perfect, but it's fairly accurate. Now we're told that we are to predict the swimming time given the pulse rate. So we need to find a least squares regression line for this purpose, and then determine how accurate our prediction was. So the least squares regression line for predicting time given pulse will not be the same as the one predicting pulse given time, because what our x and our y variables are have been switched. So if you actually go into your calculator and calculate the least squares regression line, but you switch the second and the first list, so now what your explanatory and response variable are have been changed, you will get this new equation, which therefore allows us to predict the time given the pulse. So that's what I've done here, and we come up with about 34.37 minutes, which is very close to the actual time of 34.3 minutes. So this is a fairly accurate prediction here, only 0.072 away. So finally, Part D asks us why there needs to be two regression lines. So the reason pretty much boils down to that what the explanatory and response variables are, your x and your y, were switched. So in one, time is the input, and in the other, your pulse is the input. So you actually need to have a completely different equation, because obviously you won't be able to put in pulse and get out time for the same equation that you can put in time and get out pulse. So if you were to actually just algebraically switch your x and your y and solve for the new y, you would come up with this new equation to use in part C, but I just did that using the calculator. So that's a pretty basic summary of the basic question. So the advanced question on Quideo number 2 gives us a data table comparing the capacity in terabytes of a hard drive to its price in dollars. So it's asking us, without a calculator, to write a regression equation and to define the variables that we use. So this part's fairly simple because it actually gives us right here the intercept and the capacity coefficient. So right off the bat, if we plug this into our form of y equals a plus bx, our intercept being a and the slope being b, we come up with y hat is equal to 18.617 plus 103.929x, or in other words, the price is equal to 103.9 times the capacity plus 18.617 as a flat fee, making sure to clarify that price is in dollars and our capacity is in terabytes, or TB here. Part B asks us now to explain what the slope actually means, as well as the y-intercept in context. So the slope is 103.929, which means that for every one x value, the y value will increase by 103. So in this situation, that means that our x value, the explanatory variable, for every 1 terabyte that the hard drive capacity increases by, the price of the hard drive will go up by approximately $103.93. So the slope is just telling us that how much the price is going to go up for each data unit there. The y-intercept, which is 18.617, means that hypothetically the price of a hard drive with 0 terabytes would be $18.62 approximately, which is obviously, I don't think anyone would be selling a hard drive that has no data on it. So this is kind of just a hypothetical situation explaining that there's kind of a flat fee involved with the hard drive, whether that be, the shipping costs, the labor, the materials, but pretty much every hard drive is going to cost more than this and go up by an amount proportional to about 104 times the amount of We're then asked to use the equation we have to predict the price of a 3 terabyte hard drive, which is fairly simple. All you really need to do is plug that capacity that it gives you, 3, into the regression line that we created, and it predicts a value of about $330 that should cost. Part D then states that Shaheen found a 3 terabyte hard drive for $300, and it's asking us whether or not this is a good buy. So according to our regression line, the price should be about $330. So if he's able to get it for only $300, this is definitely a good deal. He'd be saving about $30. So that is less than I guess, would be expected for a hard drive of that size, so definitely a good deal. The final AP question is talking about the relationship between wind velocity in miles per hour and the energy production of the windmill in amperes. So it gives us this calculator output screen which has r squared values and gives us sufficient information to build a linear regression equation. So part A is asking us to use that output to determine the equation of the least squares regression line, and then to go ahead and identify all the variables. So again, starting out with our basic form of y hat equals a plus bx, and we have our constant coefficient, which is 0.137, and then we see our wind velocity coefficient, which will be the slope for the least squares regression line, and that is 0.24. So if you go ahead and plug those in, you end up with the equation that the electricity production is equal to 0.137 plus 0.24 times the wind velocity, that velocity in miles per hour, and that electricity production in amperes. Part B then asks us how much more electricity a windmill would produce when the wind velocity is 25 miles per hour versus when it is 15. So the first thing I did, or I thought to do, was to plug in both 25 and 15 and simply to find the difference, which I did there, and you get exactly 2.4 amperes. Now, in my explanation, I explained that another way you can do it is merely to multiply the slope by 10, because that will be the difference here, and that will actually give you the difference, because the constants, well, those will both go away when you subtract one equation from the other, so really all you have is your slope, and 0.24 times 10 gives us 2.4, which is the precise energy difference between those two wind velocities. The last question is somewhat easy. It's just asking what the proportion of the variation in electricity production is explained by the linear relationship with wind velocity. So in simpler terms, it's just asking what the coefficient of determination is. And we see right here that that's going to be our r squared value, and it does appear on the computer output screen, r squared 0.873. And so the answer is merely 0.873, or rather 87.3% of the relationship is explained by that coefficient of determination.